In this video, we present a process that uses 3D scanning, BRDF measurement, incident illumination capture, and digital photography for capturing spatially varying reflectance properties of real-world scene observed under natural illumination. The result is a texture-mapped three-dimensional model that can be visualized for novel viewing and lighting conditions. We acquired 3D scans of the site using a laser scanning system. 50 of these scans were aligned using ICP and combined with volumetric merging. Holes resulting from occluded geometry or weak laser return were filled with user-guided techniques. The 3D geometry was divided into 680 cubical voxels, each 4.3 meters on a side. For each voxel, we create a texture atlas to source surface colors to be computed by the reflectometry process. Finally, the geometry for each voxel was simplified into high, medium, and low resolution versions. To have the computed reflectance properties best represent the actual environment, we identified an area of the scene that exhibited a representative range of reflectance properties for BRDF measurement. We placed a calibration frame around the sample, which provided fiducial markers to derive the camera position, glossy black spheres to derive the light source position, and a reflectance standard to indicate the light source intensity. We photographed the sample at night from a variety of viewing and lighting directions, taking care to adequately sample the specular and retroreflective directions. We then fit the isotropic La Fortune reflectance model to the indicated tan, brown, and black samples within the area. The three cosine lobes derived for each sample correspond to each surface's Lambertian, specular, and retroreflective components. We photographed the site with a calibrated digital camera under a variety of natural illumination conditions. For each photograph, we acquired an incident illumination measurement at the same time, using a second camera. The illumination measurement device consists of three spheres: a mirrored sphere to capture illumination from the sky and clouds, a shiny black sphere to indicate the position of the sun, and a diffuse gray sphere to estimate the intensity of the sun. As described in the paper, images taken with the device are used to derive the full dynamic range of cloudy, partly cloudy, and sunlit illumination conditions. To compute surface reflectance properties, we first assume all surfaces have the same representative BRDF. For each voxel, we load its high-resolution geometry as well as lower-resolution geometry for the rest of the scene. Then, for each photograph viewing the voxel, we load the corresponding captured illumination environment and use a Monte Carlo global illumination algorithm to render the voxel from the camera's viewpoint under the same illumination. We then project the radiance values for the photograph onto the voxel, and we compare the rendered values of the photographed values to determine updated reflectance parameters that best match the radiance observed in the photograph. This process is repeated for all photographs viewing the voxel, and the reflectance properties are averaged together, weighted according to visibility and irradiance gradients. Once all voxels have been updated, the process is repeated to account for the resulting changes in the indirect illumination, with a complete process requiring approximately 10 minutes of computation per voxel. We applied this process to both the east and west facades of our model, deriving lighting-independent surface reflectance maps for each. With the reflectance properties recovered, we can render the scene from new viewpoints and new illumination conditions. Here we see a real photograph compared with a synthetic rendering of the model made using lighting captured at the same time as the photograph. These comparison photographs are one indication that the reflectance properties derived are largely accurate. In the paper, we also compare results to the ground truth reflectance measurements. The three-dimensional model with recovered reflectance properties allows us to create renderings of the scene from any viewpoint and in entirely new lighting conditions. This sequence shows the facade illuminated with lighting captured for a variety of times during a particularly cloudy day. The techniques can also be used to prototype artificial lighting designs for a scene, or to illuminate a scene with lighting captured from a different location.